Not working. There we go. Okay, microgrids have some advantages, some benefits. We talked a little bit about it yesterday, but microgrids can actually improve reliability. They can provide self-sustaining islanding capability, reduce overall system vulnerability, and enhance the larger grid. And at the same time, it enhances our ability to utilize renewable resources, and resulting in reducing our carbon footprint and encourage third-party investment. One of the unique things about our university, most universities are focused on analytical studies, paper studies, and we do have that. We have a lot of research in labs, we have a lot of analytical research, but we're also doing real hardware demonstration projects and helping companies jump through that valley of death to commerciality. Some quick facts about our microgrid at University of California at San Diego. It's a 42 megawatt peak, annual peak load, so it's a fair amount of load. We have over 45,000 students, faculty, and staff. The load density of our microgrid is fairly high, almost 2 times what you'd find in a commercial setting, because we are such a research-oriented facility. We have over 12 million square feet of buildings. We're building new buildings, adding new structures every year, almost $200 million a year in building growth. I mentioned here that we're self-generating about 92%. The reality is we're generating 100% of our power most of the time. There's only a few hours and days of the year where we're actually importing any power from the local grid. And the resources on system that provide that power consist of a 30 megawatt natural gas cogeneration plant, and I'll talk a little bit more about that and the efficiency of that system. We have a 2.8 megawatt fuel cell, one of the largest fuel cells at any university in the country, and that's actually a renewable. It's using biogas. I'll talk a little bit more about that as well. And then we have almost 3 megawatts of photovoltaics on campus. We have one interconnection point with the utility, so we can go into an islanded mode. We have a 69 kV substation where we interconnect with San Diego Gas and Electric Company. As I mentioned, we provide about 92% of our annual electricity, almost all of our heating and cooling. It is a cogeneration facility. It consists of 2 13.5 megawatt natural gas fired generators and about a 3 megawatt steam turbine. In addition to all that, we also have about 32 megawatts of backup emergency diesel generation. I mentioned here for islanded conditions, normally we don't use the diesel generators, but if for some reason we can't maintain integrated system operation, we do have the diesel gen sets. The cogeneration plant does provide a fair amount of steam that's used mainly for cooling, heating and cooling on the campus, and we do have a fair amount of thermal energy storage coupled with that. We've been awarded Energy Star Awards by EPA, most recently in 2010, for achieving 66% efficiency on the cogeneration plant. Our microgrid is controlled by a central controller. It was developed by Power Analytics, and it controls the distributed resources on our microgrid. We show here in this picture some energy storage systems, as well as forecasting the load and forecasting solar energy. The fuel cell is, like I mentioned, 2.8 megawatts in size. It uses redirected biogas. We actually worked a deal with the city of San Diego here to capture the excess methane gas that they were flaring off to the atmosphere. So we capture that methane gas and reform it and ship it up to UCSD via pipeline, and it's utilized at the fuel cell. And that fuel cell runs 24/7 and provides about 10%, or I mentioned here 8% of our base load on our system. So it's very efficient. It's about 42% efficiency. We have a project underway right now to add another cycle onto that fuel cell to capture the waste heat. It's a adiabatic absorption chiller. that's going to be used to generate more chilled water for air conditioning load. And that'll raise the efficiency up to about 68%, which will be one of the most efficient fuel cells of that size in the country. If you were flying over UCSD and you look down, you'd see a lot of rooftops, and almost every rooftop on campus, nearly 100% penetration photovoltaics, including all of our parking garages. Like I said, we have almost 3 megawatts of rooftop photovoltaics on campus. We are doing a lot with energy storage research. We have the 30 kilowatt hour Sanyo Panasonic project that was working with Sanyo Panasonic to demonstrate community energy storage and the mitigation of intermittency and smoothing, and also to look at peak load reduction. That was an early on project. It was one of the first community energy storage projects in the country. Right now we're working on a new project, 35 kilowatt hour community energy storage project developed by MCV Energy. And the difference here is it's much more compact design. That first community energy storage system, as old as it was in a 20-foot container. This new community energy storage is in about a 2-foot by 3-foot square, so much more compact. We are working on zinc bromine flow battery. That's funded by a CSI grant, and that's focused on demand reduction, 100 kilowatt, 300 kilowatt hours. That is going through startup and commissioning right now, in fact this week. We have been doing some research on the possibility of using used electric vehicle batteries for energy storage. We know that energy storage is going to be needed really to help us mitigate the impacts of higher penetration of renewables, and the search for low-cost energy storage is a challenge. And the state of California, we have this mandate for 1.3 gigawatts by 2020. So the search is on for low-cost energy storage. A lot of research underway all across the state to develop lower-cost energy storage. And one of the things that we've been investigating is the possibility of using used electric vehicle batteries. We know that as time goes on, we're going to have more and more electric vehicles on the road. There's going to be leftover EV batteries. Maybe there's a secondary market for EV batteries. Usually when electric vehicle batteries are retired, there's still about 80% capacity. So for a stationary storage application, volume and weight is not as big an issue. So you can stack up more packs in series and parallel to get the energy storage that you need at a fairly low cost. So we've been studying and testing electric vehicle batteries for about 3 years now, running them through their duty cycles, simulated for various stationary energy storage applications. And as a result of that, we were able to actually move forward with really the world's first full-scale energy storage system using used EV batteries. And that was sponsored by BMW, using their mini e-batteries. That project is installed, and it's currently going through commissioning and startup as well. We also have a very large energy storage project that we want to couple with our photovoltaics on campus. It's a 2.5 megawatt, 5 megawatt hour energy storage project. That project is in design right now, and we'll soon start construction on that project. We also have some distributed energy storage on some of our off-campus sites. We have 5 different off-campus sites, and we're looking at we call PV integrated energy storage at those sites. One of the other types of energy storage that we're investigating with Maxwell Labs is the use of ultracapacitors. Ultracapacitors don't store much energy, but they give a good power delivery and for a little bit lower cost than conventional battery energy storage. But they offer the ability to do PV smoothing, intermittency, which is very not so much energy intensive, and then also frequency regulation. And we're coupling that with solar forecasting, and that's a research project that's funded by the California Energy Commission. And then lastly, we do have some thermal energy storage on campus, about 3.8 million gallon thermal energy storage system that we've been using to better utilize our cooling air conditioning, cooling on campus. We're developing what we call an energy research park. This is kind of something new that we've just been, just in the last few weeks, been working on with our facilities group. It'll be in the East Campus area, near the East Campus Community Plant area. We're going to dedicate that to energy research. We have some projects with a number of electric vehicle projects. There are energy storage with electric vehicles, solar, a number of energy storage projects. We have concentrated photovoltaics projects there, looking at possibly stationing a flywheel energy storage project there. So we have a lot of future planned energy research for this area, so it's something we're looking forward to. And you can see the whole list of different things in that area, the fuel cell, the ZBB flow battery, it's all in this area. Then we have some research going on electric vehicles. We currently have about 25 eco-tality blink charging stations on campus, and those are conventional dumb charging stations that just charge on a flat dollar per hour basis. But we also have smart charging, a project in smart charging that we're doing with RWE, which is RWE is the second largest utility in Germany, and they also have electric vehicle infrastructure in Germany. And we're using the ISO 15118 standard for inter-car communication and charging. And one of the things we'll be demonstrating with the smart charging project is time of use pricing for charging. So actually take the Cal ISO locational marginal pricing and then scale that up for retail pricing, and then give the customer an incentive to charge when the price is low, and when the price is high, they'll be discouraged from charging. So, and we're hoping that we'll be able to have what we call a solar happy hour, where we have 3 megawatts of solar on campus. We got excess generation. Charge up your car, you know. And then we have some DC fast charging, and we're doing some interesting things with DC fast charging in some of our research projects, looking at how to reduce the demand charge. That's one of the things that's really making DC fast charging difficult. We have a lot of tours on campus. We give tours of our facility almost every week. We have the 3 assistant secretaries in the Navy recently, and regulatory dignitaries, and even journalists. So lastly, I'd like to just say in closing that, you know, at UCSD we've been trying to do what we call lab to market. It's not just research for research's sake, but actually trying to do projects that move the needle and move things from research to commerciality. And we call it the living laboratory. It's a laboratory that's not just in a room somewhere and somebody slides a pizza under the door. It's a laboratory where we can actually demonstrate real projects on the grid. We own and operate the grid, and we have, because of that, we can do a lot of things that can't be done elsewhere. And so this presents a really valuable research aid. So that's it. I thank you very much for your time today, and that's in closing.
All right, we have a minute or two probably for a couple questions for Bill. So let's start with you.
Just 2 very quick questions. One, given what a potentially unique asset this is, have you ever looked at opening up your infrastructure to young companies that need a proving ground and have a hard time getting the time of day from the places you used to work?
Yeah. I won't go on that second part, okay? But the first part, yes, Soitec is a good example with this concentrated photovoltaics. Is a really good example. They came in with garagetronics, basically working out of their garage. They had this idea on concentrated photovoltaics, And with this inverse temperature relationship and passive cooling of the photovoltaic chips. And so our engineering department worked with them. We built a first unit. It was a 7 kilowatt unit, and it worked very well. And they've moved that from initial product of 7 kilowatts to 28 kilowatts. They were later bought up by Soitec, which is a French company, and they later signed contracts for over 300 megawatts of PV. So that's a good example, I think, of what you're talking about. And a lot of our projects, we've worked with a lot of startup companies with ideas. We very much welcome that.
Okay, and just one very, very specific question. You mentioned the zinc bromide battery. How much work do you do in terms of sort of safety and environmental ramifications of working with different electrochemistry dynamics?
Well, safety is like one of the big concerns with energy storage. Fire safety, chemical handling safety, spill response, mitigation, that kind of thing. We've taken great pains and efforts to ensure that the research that we're doing is safe research, but at the same time allows us to test new concepts and new research. And it's always a balance between the two. But we have, in the case of the zinc bromine flow battery, we do have mitigation measures in place to neutralize any spills. We have three levels of protection there. We have 2 forms of containment, actually 3 forms of containment. We have leak detection and alarms and self-shutdown as well.
All right, 2 more questions, one here and then one back there. Let's go.
Hi, I wonder with all your research whether you could comment on what you found to be the cheapest way to reduce your peak. Would it be, for example, the gas-fired cogen, or would it be the thermal storage or some other approach?
One thing I didn't mention is that we do have about 5 to 6 megawatts of automated demand response on our system. Not that that's the preferred method of load reduction, but we do have that on campus. And actually, we can dial in, we can actually have control of all of our thermostats in all of our buildings on campus. And we've got that tied into a controller, and we can automatically drop that temperature down, and we can drop 4 or 5 megawatts off in just about 10 to 15 minutes, campus-wide.
All right, one back there, and then we will take one final over here.
Catherine Von Berg with OES, Optimize Energy Storage. I'm wondering if you could address the, let's see, the 2.5 megawatt, 5 megawatt hour installation under the SCIP program, quote unquote, Advanced Energy Storage. You mentioned the ZBB and fuel cell installations, which range anywhere between 30 to 48% inefficient. And so under the SCIP program, I'm wondering if you could address, one, what is the advanced energy storage that you're using? And you say the project is underway. Are you accepting proposals from startup companies that provide truly efficient, clean, advanced energy storage?
Okay. I can't see where you're at, it just lights in my eyes. But I will say that we went through an RFP process almost a year ago. And we went through a selection process. We selected a vendor. The SGIP requires that it's a commercial venture. So the 2.5 megawatt, 5 megawatt hour system is not really a research project per se, but it's a commercial system that will be integrated with our microgrid to capture the solar and maximize overall system efficiency. And so we've kind of already gone through that RFP process, but we're always open to talking to people about the energy storage. We're constantly doing research. In fact, right now we're going through proposals with CEC and DOE. So please feel free to talk to me later on.
All right, one last question, and we'll try to keep it quick so we can get moving.
Martha Simcoe-Davies, I'm the Director of Partnerships for Energy Systems Integration at NREL, and I just want to commend you. You've made some tremendous progress on all those projects. I'm wondering a little bit to the vision in the near term as well as long term for energy systems integration, where you see yourself heading and what do you see as the biggest challenges moving forward?
Well, I think energy storage, that's what you're asking about, right? Energy storage is still somewhat, probably get chastised for saying this, but it's still somewhat an immature technology, and there has a lot of shakeout that's going to occur as we go through this process. And it's not clear exactly which way it's going to go and what we're going to end up with. But I think that it's going to be a combination of distributed energy storage to address the issues down at the distribution level, as well as some bulk energy storage to deal with the issues of resource adequacy statewide or nationwide, I guess, even.
Great. Thank you very much, Bill.
You bet. My pleasure. Thank you.
All right. As the next panel comes up and gets ready, I just wanted to make a quick announcement.